All right, welcome to the session. It's very exciting to see all of you at the Microsoft Ignite event. Before we get into the content, a quick question. How many of you are new to Azure Cosmos DB? How many of you deployed stuff on Azure Cosmos DB in production? A few. Great, it's exciting. The content here today covers both. If you have gone all the way from a POC to production, I'll share some best practices that can probably help you a little bit more. And for those of you who are new in the audience to Cosmos DB, the session will cover best practices that can get you ahead in your implementations. Okay. Just a quick intro about myself. I am Surya Nanduri. I'm an engineering manager at Microsoft in the Core Services Engineering and Operations team. At Core Services Engineering and Operations team, we build, deploy, and manage applications that run the business of Microsoft. And these applications are used internally by the employees and also by our customers and partners to do business with Microsoft. With that, let me get into the content. Today, the session objectives are the three things that I want you guys to take away. Is number one, how do you model your Cosmos DB collections and determine the throughput? And second, how do you do horizontal partitioning to scale out? Third, how do you make the right trade-off between consistency and performance for your Azure Cosmos DB implementation? And we'll apply these concepts to a real-world example from our own learnings from the project that we have done, which is enterprise time tracking. So for those of you who are new to Azure Cosmos DB, a quick intro. A few things that Azure Cosmos DB provides is number one, turnkey global distribution. Second, it can horizontally scale out, which means you can move from small amounts of data, small number of requests, to large amounts of data and very, very high volumes of requests. So you could horizontally scale out without any downtime. Number three, it's a multi-model database, which means we support key value, column family, document, and graph. And on top of this, we have different APIs to access the data. And today, all the best practices that we share is going to be on the core SQL API that Cosmos DB provides. And majority of the implementations that we run into with our customers are implementations on core SQL API. A little bit of background on the use case that I'll be referring to in today's presentation is about time tracking. And we rolled out this application to the enterprise services users of Microsoft. Basically, services employees work on customer sites, on customer projects. They log time, and this time they logged is used for billing and compliance reasons. So it's a mission-critical application. If it goes down, the problem is we'll not be able to invoice our customers, and we'll be non-compliant. So it's a mission-critical service that way. And why is this a good use case for Azure Cosmos DB implementation? Because the user base is globally distributed. Microsoft is a huge company that's across the world. And there are many different query types that the application has to serve up. So it's a really good use case. So with that, let's dig into the design of what we have done. Determining throughput. Throughput basically is the cost of doing an operation, right, in simple terms. So how do you determine the throughput that you need from Azure Cosmos DB? Simple steps is number one, let's define throughput, and then I'll walk you through the steps. Throughput is measured in request units. Basically, if you're scaling up in a relational DB sort of scenario, you're either bumping up the memory or the CPU or IOPS. What Cosmos DB does, it abstracts all those three and gives you this logical way of defining the RUs, and that's how you measure the throughput. And you can provision throughput at two levels. One is at the database level, and second one is at the container level. When you provision at the database level, all the containers in that database get equal distribution of that throughput. And if you put provision at the container level, then you have more control over the throughput that you want that container to have. Okay? So it's a design choice that you could make based on what you do in your application. Second is identify access patterns. Is your application read heavy, write heavy? What's it like? So it's very important to know that, because a lot of design decisions are based out of what sort of access patterns are there in your application. Number 3, if it's a read heavy application, make sure you understand the query patterns. I will cover partition in the next section. Basically, you want to know what are the in-partition queries you're running, what are the cross-partition queries you're running, how expensive are these, and how can you optimize your throughput, and things like that. We'll cover that in detail in this section and next. And last, unless you run a POC, you wouldn't be able to determine what sort of throughput you need. So I highly encourage you guys to run a POC before you do an actual Azure Cosmos DB implementation. That will allow you to understand what your patterns are. And then one thing to avoid is don't do analysis paralysis of that data, because in Azure Cosmos DB, you can always course correct without any downtime. So calculating throughput. So we ran a POC with a load test of 27,000 users, and then 5,000 approvers who are worldwide. And the workload is, as you can see, read heavy. It's a 2:1 between reads and writes. And when we ran this POC, this is what we got from Cosmos DB metrics. Basically, if I explain this out, the y-axis is the throughput in RUs, and the x-axis is the date. As you can see, much of the throughput is around the 500 to 1500 RUs range. And then you see spikes, which go up to 7,500 RUs. Okay? So that's what we got out of it. So what do you make out of this? And how do you set your RUs? So a pop quiz. What should be the throughput in RUs per partition? Any guesses? Yes. B? Okay. Any other guesses in the audience? Any A's? It depends. Okay. So let's figure out what the answer is. All answers are valid, but what is the most optimized answer? Let's figure it out. Let's make some design decisions on the fly. And I'll reveal the answer at the end of the next session. Okay? So let's see, you saw some towers up there in the graph. Let's analyze why those towers are there and why those queries are taking a lot of throughput, a lot of RUs. So when you analyze queries, you can analyze with two things. One is Azure Diagnostics, which is basically out of the box Azure provided. So it helps you find out what are the queries and how much RUs each query is taken up. But due to PII and things like that, you don't get the exact query. You get a masked query when you get into the Azure Diagnostics. If you want to see the exact queries, App Insights can give you that, because this is at the application level. You can log what sort of query you're running, and then couple that with Azure Diagnostics to see how many RUs it's consuming. Okay? So with that, let's analyze this query. So the query that's consuming the high number of RUs is get all time entries to be approved by Sandeep. As I said in my use case, there are submitters who submit time, there are approvers who approve time. So in this case, when the approver Sandeep is asking for all the time entries that that person needs to approve, that's taking a lot of RUs. So let's see how many RUs this is taking. So it's taking about 959 RUs at peak, and on an average it's taking 50 RUs, which is pretty high. And number of requests exceeding capacity is, I set the capacity at 500 RUs for the POC. So it's 180 queries are exceeding the capacity, and when it exceeds, what Azure Cosmos DB does is it retries. It retries for 9 times to give you the result before it says, I can't do it. And the error code that you get is HTTP 429 when it exceeds the rate limit. So we see a couple of issues here, right? One is, because it's taking a lot of retries, it's poor performance of the query, and high cost because of high RU consumption. And that's why you see the towers up there. So what do we do? How do we optimize this? Let's look at it. And that gets into the next section called partitioning. And this will help us not only scale out, but also reduce the number of RUs some of those queries are taking. So let's look at the document for the use case today, which is a labor document, and it has certain attributes in it. I use the embedded model here. There are two models, embedded and referencing. You use embedded when it's a one-to-one, one-is-to-few between the main object and the embedded objects called the assignment details and approver details. If you have one-to-many or many-to-many, you use referencing. So let's look at the best practices for selecting a partition key. How do you partition your data for horizontal scaling? Number one, the storage distribution has to be uniform. So basically, it's like this front row seats, right? If it's uniform, then it's better for performance and things like that. And high cardinality. Make sure there's uniqueness of value when you are selecting a partition key, so that you get the most throughput. Third, good distinctiveness at any given time. So these are the three factors which you can use to select your partition key. And let's look at some of the candidates in that list which are eligible for partition key. So we looked at submitted by, submitted date, and assigned approver as the three partition key candidates. And we ran it through these three different best practices that I just mentioned. So if you look at submitted by, storage distribution uniformity is very high, okay? Because if you're partitioning by username, all the data that user enters is in that partition, and likewise for other users also. Cardinality is very high, it's unique, that does not change. Number three, distinctiveness at any given point of time is high. Let's look at another example. Submitted date, storage distribution is not very uniform. Why? Because today it could be a high traffic day. Tomorrow in the US it's a working day. In India it's a holiday. So in that particular partition, you would not have enough data, and it's not uniform across different dates, right? So it's low. So given that criteria, what we selected is submitted by becomes the best partition key, based on those best practices for selecting the partition key. Now let's see how Cosmos DB divides the data based on this partition key. So that's how Cosmos DB logically partitions based on the username. Because I have 27,000 users, it divides the logical partitions into 27,000 logical partitions. And underneath that, there are physical partitions, and Cosmos DB gave me 10 physical partitions. So when you run that query, select star from collection, where submitted by equal to Surya, it directly runs on the Surya collection, and the response time is instantaneous because it's a direct read on one logical partition. Okay, it's called the point query, and the RUs taken for read are 1 RU for 1 kilobyte of data. So this is the fastest Cosmos DB can get. So let's see a second example of a cross-partition query. So here, approver is trying to approve all the labor that is submitted where he is the approver, Sandeep is the approver. So select star from C, where assigned approver equal to Sandeep. So what does Cosmos DB do in this case? It runs that query on every logical partition to find out what are the labor entries, those are entered by those users, where the assigned approver is Sandeep. So the query is run on 27,000 logical partitions. And that's why you see an average RUs of 50 RUs and peak usage of 959 RUs, because it's running across 27,000 logical partitions. So what do? So let's see what the total RUs consumed in this case is before we figure out what do we do about that use case. So document write takes 5 RUs because Azure Cosmos DB replicates all the writes, and 10 writes per second, so total is 50 RUs. For assigned approver query that we just saw, it consumes on an average 50 RUs, and it's 100 queries per second, so total is 5,000 RUs there. And then for the point query, it's 1 RU for 500 queries per second, so 500 RUs. If you total all that up, it's 5,550 approximately RUs, okay? Let's see how we can optimize this. So I'll introduce a concept called change feed. So relook at the top query. Let's relook at this. Now, Cross-partition queries are okay if they're spaced out. But if they're too frequent, it will cause high number of RUs, like you saw in the towers in the graph that I showed you. So what do? Change feed is the answer for that. So basically what change feed does is, so this is my first collection, which is the labor collection, where it's divided into 27,000 logical partitions. Now I do a change feed on this. So basically I read the events, I write an Azure function, and pump those documents into another collection called approver collection. Okay? And then the partition key there is assigned approver. So in the approver collection, because there are 5,000 approvers, Azure Cosmos DB divides that into 5,000 partitions. And now partition key is assigned approver. And it's totally okay to have more partition keys. That makes your application more scalable. We'll talk about storage because we are duplicating data. Do not worry about storage, because storage cost on Azure Cosmos DB is very, very less compared to the compute cost. Okay? And then if you're worried about storage, then you can use this feature called TTL, time to live for a document. If you set that at 1 month, the document gets deleted after 1 month. So that way you can clean up the storage. So in this approver collection, the partition key is assigned approver. And here, because assigned approver is in the where clause, it directly runs on the Sandeep logical partition key. It becomes a point query. So you just changed from a cross-partition query to a point query by using change feed and another approver collection. So let's see what the cost estimate of this is. So the document write, which did not change from earlier, 50 RUs. Now when you're reading the document from labor collection and putting it into approver collection, the read is 1 RU and the write is 5 RUs. So the read is 10 RUs, write into the new collection is 50 RUs. Now assigned approver suddenly became a point query from a cross-partition query. So it's only 1 RU consumption. So 100 RUs is the total. And submitted by query remains as it is with 500 RUs. The total you get is 710. So you saved 8 times the number of RUs than what your design was previously. So you're at 5,550, all the way you're at 710. So you pay for each RU, and you just saved a lot of money. So remember the pop quiz? How many of you guys had A as the answer? Okay. So the correct answer is somewhere around A. So that's what we did. But as I said, all answers are correct, but you need to find the right optimized RUs so that you pay less for better performance. Okay? So let's look at another concept called consistency level. As I said, Cosmos DB provides turnkey global distribution. How do we replicate data and make sure that we get high availability and high performance for our application, right? So make the right trade-off between consistency and performance. Basically, our use case was write region is West US and read region is several. And here's the Cosmos DB collection and the partition key is submitted by. It's very important to understand what your requirements are to determine the right consistency level. So the requirements for our application are user always gets the latest. So when you're submitting and you're making edits on your labor, you want to make sure that you're editing the latest copy and not an inconsistent copy. And when you're approving, you always approve the latest edited labor rather than approving an old copy. So those are a couple of requirements. And third is because we are in an enterprise sort of situation, we have dependencies on other enterprise systems. So let's look at our POC results. And Cosmos DB offers consistency levels from strong all the way to eventual. And in between, it offers 3 extra consistency levels. So let's go with strong and see what the results are. When we put strong, here the availability is low, because each time you write, it has to go replicate into all the regions. And after all the replication is done, that's when it says, okay, I'm done, and here's the new copy of the data. So that's not very highly available. And second is, performance-wise, it's slow. So slow response times. We're not talking about a huge number of seconds and minutes here. Compared to the other consistency levels, these are a little bit more slower. And the other thing is, it's twice as expensive than session consistency. So that's the cost factor involved. So let's look at bounded staleness. Bounded staleness means you are reading K versions of data which is late or T times late. So basically, again, we looked at this option, but the con here is still availability is low, performance is high, and the cost is also very high. So it doesn't really work for us. Then we looked at the session consistency. Here, when you're doing a write, Azure Cosmos DB gives you a session token, and if you're reading with the same session token, then you'll get the latest written copy. So with that, what we could do is the system guarantees the latest labor record. That's what the approver wants to go approve. So this works really well for us. And from a cost perspective, this is 2 times less cheaper, less expensive than the bounded staleness and strong consistency levels. Fourth, consistent prefix. Basically, Cosmos DB guarantees the order in which the versions are given to the read, but it does not really work for us because approver has to always approve the latest copy of the data. So it doesn't really work for us. Eventual, Cosmos DB does not guarantee the order. Again, this does not work for us because you have to edit the latest approved, latest copy of the labor record. So with that, what we selected was session consistency. Again, from an availability point of view, we got high availability. From a cost point of view, it's better. And third, from a performance point of view, it's faster. So that's how you select based on your data load, your patterns, your requirements. You can select which one works for you. 80% of our customers and users use session, but there are situations where you want to use other consistency levels. And here are the metrics and SLAs for our application. We got 27,000 users on it. Azure Cosmos DB provides less than 10 milliseconds of latency at 99 percentile, which is super awesome, and a 5 nines availability, which is the best of any service on Azure. So it's awesome. And for our application, the response time is less than 2 seconds because we are running on this world-class Azure Cosmos DB infrastructure. And the cost savings are 50% for us compared to our earlier implementation on Elastic DB. So with that, you guys want to see a little demo of our application? And the cool thing is we are launching this at the Ignite for all our users. Any volunteer in the audience on who can help me launch it? There's a goodie. Can come over. All right, what's your name, sir?
Espen.
Espen. Fantastic. It's a mobile app, Espen, so let me open that up for you. Great, so this is the home screen that our services users get. Basically, it's saying, hey, my name is Mast. Hey, Ho Young, recommended labor entries for you based on historical labor entries that I've made. And here's the meeting and events. So basically, you can enter time against the projects, which is the MCS tag here, and non-projects, which is like training sessions that we're in here. So we just attended a 20-minute session. Yeah. So let's enter 20 minutes as the time. Let's click this here and do the honors of doing the agree and submit.
Agree and submit.
And there you go. And I got the same Wi-Fi connection as all of you have. And the labor is submitted successfully, and it shows up in the My Labor category. So this morning I attended Satya's keynote. Oops. Oh man, that was a bummer. We'll do it again, Espen.
Yeah.
Okay. So here's the mobile app. It basically says, hey, Ho Young, which is my mass name in the application. Here are the recommended labor entries for you. So we are attending a meeting event here. So we'll click this, and it's a 20-minute session. So we'll enter 20, say yes. And then do the honors again. Thank you, Espen. And boom, labor gets submitted. So that's what our services users are mobile. So it's a very handy application for them. Anywhere in the field, they can go enter their labor, which is a daily activity they need to do. Thank you for helping me launch. It's a small goodie for you. Thanks, Aspen.
Thank you.
Appreciate it. So with that, here are a few resources on Azure Cosmos DB that you can look up. It has practical exercises, labs, a lot of documentation, and some case studies that you can go through to learn more about Azure Cosmos DB. And stop by our booths. We are the core services engineering team. And go to IT Showcase. There is a white paper written by Kurt Delbini on how we are digitally transforming IT within Microsoft. It's a very good read. I encourage all of you to go through it. And yeah, thank you for attending the session. Please evaluate the session. You should get a notification on your mobile app. Your feedback is very important to us to make sure we continuously improve. Thank you, and I'll be on the side stage here if you have any questions on Azure Cosmos DB that I can help answer. Thank you for being a wonderful audience. Appreciate it. Have a great Ignite.